in detail, ask me everything. As I told you, results are not good. Don't be shocked. I mean, there are a few good grades, and most of you got C, which is not good. I'm not happy with it. You can go 2 grades up. And I hope most of you will, indeed, because I know that for a few of you, I know it can be better. The quiz, maybe you found a bit tricky. Maybe that's what confused you. It was different kind of, not just solving the problem, but so we will go through it. I need exams in the end as a proof of your grade in the end. So you can look, you can copy in your book if you want, in your notebook, but in the end of the class I'll take them. So. See very well the problem. There is no excellent. And you know, I mean, we actually gave you, it was supposed to have 20 points. It was possible to get 22 in the end. We gave 1 extra point, I mean, we put, not 22. We gave 1 extra point in the problem, so 6 instead of 5, and we scaled everything by 1 point. So it was 19, scaled to 19 or to 20, to increase the percentage, to make it a bit better. No, making a few silly mistakes, it's fine. It's normal. I mean, if somebody had everything solved, I'd be really worried because it's not a sign that, also, few of you will find access to the previous year's exams. If you have them, please share them with your colleagues. I can give you 1 more from what I was giving. So it's not fair that half of the class has, half not. If you have, please share them so that you all have kind of the same chances of getting. But my advice is not to go too much through the previous exams. You will learn the trick which was in that exam, but I'm really putting lots of effort to make new problems. I'm trying to test really if you understood, not if you remember from the previous exam. So maybe there'll be like a few same, but still not enough to pass by learning from by working only on the previous exams. It's true, we did ask a little bit of knowledge out of the course. I asked Nadia, she said that she did explain alkaline. And it always has to go a bit beyond. It's hard to make a problem, but we scaled. So for each of you, we allowed for 1 problem not to be understood, let's say, because we put maximum to 19. Yeah, there were a few tricks. I think you all have good English. We always had somebody with whose English was so-so, and it was hard to judge that person's knowledge, understanding, because there was always English entering also. But I think this group is you're all very good in English. Tell me if not. Tell me that, then during exam I can at least come and try to explain in different words the problem. That might help. So I would suggest we do like in the tutorial, similarly, we solve 1 by 1 and discuss. The first one, surprisingly, not many got right. I was expecting it 100%, the problem.
I was confused by looking at the instructions.
It took maybe 1 minute, 2 minutes, 3 minutes of looking. Don't know. Did you find it difficult? Do you know what is formula unit? Somebody did ask me actually. You asked me, and you got it wrong. You just, from the knowledge of the unit stuff, you have to know how the atoms are shared in a cubic cell. Okay. Would you come to the blackboard to solve it? you got it right.
I got it right, but I actually just somehow guessed it a bit.
It's okay, no, I mean, don't worry. It's hard to draw the blackboard, that's one thing. But what do we see? How many orange colored atoms? Okay, orange colored at the corners. So at the corners, how many?
We have 8. Like,
8 on each corner. Atom at a corner belongs to one unit cell by 1/8.
Okay.
So we write 8 times. So orange, no, it's 8 gold, no? 8 times 1/8 plus. Then we have some at the edges.
What do you mean edges? The faces?
The faces, sorry, I meant faces, sorry. Faces.
So at the center of the faces we have 6.
6. So can you continue? 6. And if the atom is at a face, it's shared between 2 unit cells.
So it's 1/2. Oh,
Yeah.
sorry.
You can continue, so it's and this is all orange. So this comes to how many?
It's gonna be 1, and then this is 3.
So we get 4 A atoms. Okay, let's see about the B species.
Okay, so for the B's,
I mean, maybe you did not do this exercise exactly, but if you understood the whole logic of the unit cell, how atoms are shared, that should come out quite naturally, but okay. Okay, B,
so they
are all inside.
inside. Yeah.
They're not shared between different unit cells. So
Yeah.
how many? 8 of them. B, 8 B. So it is A4, B8, or this is a weird way to write. So AB2. Everyone understood. So this was not supposed to be any trick question. There were a few which I was actually going to ask for excellent, for the highest grade. Yes. Yeah, welcome to it. Yeah, that was maybe a bit of English, but that was not asked. Okay, we'll come to it slowly. This was not supposed to be trick. I'm sorry to get it as a trick because, I don't know, it wasn't meant. William.
Yes.
So, assigned face-centered. Can you come to draw it? This one was a bit more difficult than the first one, which was supposed to be easy. I'm sorry, because many of you lost the point in the first one, but it was meant to be easy. The second one was a nuance more difficult, because you had to, okay, so what is it? Face-centered, side face-centered cubic. So it is not face-centered, it's just on the sides. Doesn't have these 6 atoms on the middle, at the center of the side.
Yeah, they explained it.
Just
it is
4 of them.
The normal simple cubic with addition of these points at the center of the 4 vertices. But at the center of the 4 vertical faces.
And you will get very similar in the exam, in the final. So it's good to memorize a few things, but that's not going to bring you points mostly. Actually, I noticed that a few questions were similar to the previous year's exams, but opposite thing. And you went for the thing from the previous year's exams, solutions. Okay, good.
And this face, this one, and this one.
Nice, careful drawing.
This one.
Okay, so
Okay, this place.
what is the definition of a Bravais lattice?
Bravais lattice?
You remember?
Yes, I remember. It is one for which we can get the primitive vectors whereby you can
Independent,
linearly independent.
Okay, and write any lattice position in this form. Vectors. That's important. They're all vectors. Yes. Okay, the question is, can you find 3 independent vectors, primitive vectors, to describe all lattice points here?
No, I couldn't.
You couldn't, okay, that's correct. I mean, if you have a face center, then you will have to 3 faces, the easiest.
Yeah.
Here, if you take 2 to the vectors, to these, you cannot describe the cubic structure anymore. So this is a bit weird because you have to try and not reach the solution. It's easier if you try and reach, but okay, this is,
So,
but it was impossible. I mean, I hope you tried. Each of you should try, and I mean, if you haven't read the exam, make an exercise and try forming. Clear to everyone? This one? Yes. Also, this one had quite a few wrong solutions. Voila, would you come to solve the next one? Rectangular Urica. This was a little bit of a trick, which I hope that you would understand, but not everyone did. Voila, can you come? Here, we have a rectangular lattice. Let's make it in 2D, extend. Okay, you guys make much better drawings than me. Okay, so this is A, this is 2A. From this point, let's count first neighbors. From this, yeah, from here, how many first neighbors are the shortest distance?
Here, 1, 2, just
First, 2 first neighbors, 2 nearest neighbors. And how many second nearest neighbors?
we have this one, this is 1, 2, 3.
No, this one is further.
Yeah.
This one is at 3A square, okay, square root. This one is further.
1, 2,
And this is 2A also. This was a bit of a trick.
Yeah.
I mean, I told you to practice with the lattices to count, and don't ever underestimate the problem.
Yes.
That happened to me, to solve wrong. I gave previous year some easy exercise. I said, oh, it's too easy. And then I had it wrong, so the student would solve it. Oops, I made a mistake.
Actually, we never go outside those boundaries.
I mean, don't ever underestimate. It might be too easy, but there might be something you're overseeing. Okay, so how many seconds? 1, 2, 3, 4. It's 1/2. Thank you. What is next, Harriet? This one. Will you come? It is the packing factor between 2 tetragonal lattices. First they asked the ratio. I thought, no, it's too difficult. Let me just ask which one is larger. You got it, but not everyone. There were still mistakes in this one, which... Can you draw a tetragonal lattice? It is like rectangular, just extend. I mean, it has a 1 square and 1 rectangle. Yeah. So it's important to understand which lattice you asked. This one I thought I took, but actually even defined here. But it's more difficult. Yeah, it has 1 square or 2 squares and 4 rectangles. I mean, so I would draw a rectangle and then, and here it's square. That's the typical way to present. So A1 and A1. Yeah, this is A2, they are the same. And this is A3. And it says in the first one, A3 is twice this. In the second one, it's 4 times that. And it's asking for the packing factor. Do you know the definition of the packing factor? now one could go and exercise to do the whole thing, find the number, but why would you? The question is between this and then longer. So let's make it even longer. Okay, not perfect, but so this is the same, and A4 is larger than A3. What did I change between these two lattices? Did I change S occupied? What is the radius of sphere in this one? It's defined by the first neighbors. Okay, this radius occupied, so the sphere, is defined by the nearest neighbors. The nearest neighbors are in the plane. This is the, so it will be here, no? Until they touch in the plane. Okay, you can imagine. So it's defined. This remains the same in the two lattices. But the total volume, actually this is volume now, not the total volume. The total volume is changing. It's becoming larger here.
Yeah.
You divide by the larger number, so it's a smaller packing fraction. But so the answer is that the first one has larger. But it's very logical. You can do it even without much thinking, because packing factor gives you how efficient the packing is. That you have more occupied space in unit cell. So if you make the shape ugly, extended or less symmetric, you're losing it. The more symmetric the cell, the higher the packing factor. So you could solve this without even drawing this. Just knowing it's going out of symmetry, I mean making it more verse ratio, let's say, has more empty space. The next one, Nishan. Oh, again, the vectors for you, good. This one actually, there were many people who solved wrong, gave two answers. Here was just one answer, really. And it was quite incorrect to give half point on this one. So, no, the quiz was quite bad actually, but I was happy with the problem. Obviously, you all did practice similar problems, and I was happy with the problem. You all went quite far, let's say, in the problem. But the quiz was a surprise. What are you doing?
Okay, so we have been given two primitive lattice, and we have been asked that which of the following cannot be reciprocal lattice vectors. So what I'm trying to do is, I'm trying to the connection between the any vector in the Bravais space and the reciprocal space is let's say r dot z equals to, it should be 2 pi into n.
Or, you know, what is the rule? If you have two primitive lattice vectors, we want to find the primitive reciprocal lattice vectors. This is the option. So there A1 this is correct. But A1 times B2 is 0 with the opposite one. So the simplest way probably would be just to try this kind of relation. It can be n, yes. Just try and see. If one vector gives non-zero for both vectors, cannot be.
Yeah, because this...
Or gives 0 for both. I mean, this should be fulfilled. So, just try. I mean,
just did a more elaborate one.
Or you could actually, or you could derive the B1 and B2. Whatever you prefer. This one is a slightly bit longer, but I'm just warning you that the first vector was not the simple primitive reciprocal vector. It was a combination of the two. So, Okay, let's find V1 and V2. Okay, I'm seeing people a bit lost. Let's try V1 and V2. Okay, just find them. Whichever you like, find V1, V2. It's the safest thing to, not to show the shortcuts if the brute force is not clear.
I actually wrote a general R in terms of A and B, A1 and A2, like this, and just checked with all three. If
Yeah, can we just find the vector?
Yes,
The simplest way, because I didn't see people following what I was saying, so just to be sure that it's not lost, this is an easy problem. This I was hoping that everybody will get right, at least by brute force. I mean, there were tricks to use, but you could do it brute force. And you see right away it's the B solution.
so
You could also find it by finding the third vector being CZ and multiplying whatever you prefer. It's the same. Do you get it right? Okay. Okay. You follow it? One can also construct these vectors purely geometrically. You draw them and construct by being orthogonal, by seeing which angle gives positive, because A1 times B1 is 2 pi, not minus 2 pi. So you can find either this one or this one when you draw like orthogonal to the other vector. It's just a bit of practice. You can do it without calculation. Okay, good. And now from here, it's relatively easy to find
okay, so any vectors in reciprocal space we should be able to write in terms of the
B1, B2.
B1 and B2.
So just check the solution A. Is it okay? I mean, you find the vectors.
Okay, 4 pi by A. 4 pi by A. Can we write it in terms of 4 pi by A? Okay, pi by A. So, 4 pi. 2. 2b1 plus b2. So if we do this, it will be 4 pi by a minus 2 pi by a plus 2 pi by a.
So just write also xy,
oh, what?
xy components.
Oh, I just
No, just add them. Yeah, the first part is x.
The first one.
oh,
X, I mean,
so I'm just
okay.
like
I mean, as the components of the vector.
so 2 pi by a and minus pi by a plus
0 to
0 2 pi by a 4 pi by pi by a and
and 0.
okay, I'll just write it like minus 2 pi by a plus 2 pi by a. So it is possible.
Okay, let's write it as then the same way as before.
Okay. So yeah, it is possible to
obtain a
represent
linear
the
combination.
person.
Yeah, okay.
Should I rub this?
It's okay. Yeah, you can. Do you all understand this one? It's an easy one, which took points of not difficult. No, it's just don't underestimate the problem. Even if it's too easy, still give it additional thought. Don't go for the most obvious solution always.
Okay, the
It
second
can-
one is very obvious because the second one is just B1.
Yeah, it just be one. Yeah.
So is it clear to everyone? Because the third one, okay, the third one is pi by ax, which can't,
Yeah,
which
you
is
can
not
also
possible.
look if B is, then you cannot obtain C
So
from B.
I'll just tell you
That's
why the third one is not possible. Because in the third one we have, let's write it, open it like this, x plus 2 pi by a y. So let's not worry about this first for some time. We want pi by a in as our x component. This will never give anything in the x component because this is 0. To have pi by a in the x component, we should have 1 by 2 b1. But we don't
be
generate
smaller
our
than-
reciprocal lattice vectors like that. It has to be
Multiple
n1
of B1
b1 plus n2 b2
and 2 and 2 should be integers.
n2
No?
belongs to integers. So we can't have half integers or some other rational, irrational numbers. So there is no way we can get C out of this
Yeah, okay.
B1 and B2.
Very good, thank you.
Should I?
Okay, number 6 happened to be disaster. I think one got it right, or two maybe in the whole thing. And JC, it's yours.
A system has 2n plus 1 electron, valence electron per cell per unit cell, which the following statements are true. So the answer is C.
Okay, let's go one by one. Why it cannot be A?
A is false since for a system with 2n valence electrons, it has the same fully occupied bands with 2n plus 1 electron. In the statement,
It has it always. If it wasn't this always,
Excuse me.
yes.
I think I got confused because of the
Or yeah, either fully or partially.
Or partially.
So it has got one, always has
It
got.
always has more partially.
No.
It can be partially then, fully or partially.
There is
It also
also
more fully
or
or
partially.
partially.
That is
Or part.
fully. If it
I'm
was
not getting this.
fully.
It has more partially occupied bands. That's one understand. No?
I'm reading what is here.
Okay,
It
yes.
it always has more fully or partially occupied
Yeah,
bands.
fully or partially. I'm not getting it. Sorry.
So me,
Either fully or partially.
I understood that.
Yeah, either fully or partially. So it always has
Fully or
one partially band.
if
So
one
it
is
should be
true,
right. If one is true,
It should
then
be true.
it should be true.
The statement is
Yeah.
true then.
If
No, you can have 2n plus 1 Fix. Let's say n is 5. You have 11 electrons. I can put them 2, 2, 2, 2, 2, 1. Okay. I have 2n, 10 of them. I can have 1, 1, 1, 1, 1, 1, 1, 1, 2, 3, 4, 5, 6, 7, 8, 10.
This is okay.
It can happen if you have 10 valence. Okay, 10 is a bit too much, but I'm talking about valence electrons now. There is no rule. Okay, and 10 is a bit too much. Imagine for 2, it's very realistic. And just put, you're confused with the co-electrons or
No, madam.
partial.
It's not. The only issue here that also confused me
Yes.
was the word O. Because if they say O, then it
But
means
fully
that if
or
one
partially?
of the statements is true, then the whole statement is true. That's okay.
But
that's
neither
the-
is true. It doesn't have more, nor fully nor partially.
Because
I can pack them more tightly with more electrons.
So like, is it possible that one?
If the system is magnetic, it will actually have 1 electron per
Band.
band, yeah.
Because in the first option we are
So it doesn't mean if you have more
System.
electrons, you will have more bands. It can be, but most often it is. It doesn't have to be always. Nor fully, nor partially. I mean,
if we consider it with the system of two n valence electrons as it was here, then I thought that this one that has 2n plus 1 will automatically have probably more partial.
I know. Also, you have 5 electrons or 4 electrons.
Yes, 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 yes.
More likely, I would agree. Always no. I'm telling you, it can be like 4, and each has electron with spins aligned. You have a moment here. In this case, you'll have also a moment because it's an odd number.
Oh, if you put 1, 1, can't you put 1, 1, the same kind of feeling for both?
But I'm saying always, always. I'm not saying if this, always. Is this true always?
Okay, like what we did was we just filled it like up, down, up, down, up.
I know. So this was useful to clear this out. One bad thing of this year's courses, you don't have any magnetism. I'm sorry for it because I work on it. This is kind of the basis how you create magnetism. You have unpaired electrons of the same spin and they create a moment, magnetic moment. This is the origin. If you pair them, spin up together, there is no moment. So this is kind of the basis for thinking at all about it. So it's now clear why A cannot be solution, because you can have this solution, this option, this can happen. With n10, no, it's a too big number, but with n2 or something, yes, it happens. With the electrons, specifically, they are the ones which create the moment most often.
so it means that
Or F.
it is always just all the centers.
Always was the trick. B was, it always has n plus 1. Obviously, it doesn't have to be. It can be packed tightly or just by 1. And then C is the solution, yes. Here, I don't think, 1 or 2 correct solutions, and maybe even those by luck, I'm not sure. That was a disaster, this problem. Oh, this one, I forgot to bring you. Last year I brought the band structure to the class. I forgot this year. What you can have, let me just draw something. Gamma, X, and whatever. What? Let me draw the Fermi level. Something like this. What do you have at the gamma point? Here. here you have, at the gamma point, I can find the difference between the highest occupied valence band and the lowest occupied conduction band. It's a huge difference. At X, still you have a difference, a bit smaller. At this point, you have a state of the Fermi energy. What is this? Is it an insulator or a metal or? We did graphene last time, and we said that we have just one single state crossing the Fermi level, and we called it semi-metal. Semi because it just touched at one point. So if you have any state at the Fermi energy, any state, anywhere in the brilliant zone, anywhere, it's enough to have some conduction.
There is a path.
Yeah. I mean, you will have a state, an electron at the Fermi energy, which is moving more, which is usually the one responsible for transport, for all the properties, for binding, for. So this wasn't meant to be really a trick question, but it happened to me to be because very few answered correctly here.
Excuse me.
Yes.
There is something that we had in our notes that I used to answer this.
Okay, so I guess you don't have much experience and you didn't have chance to think of it, because if you had thought of it, you would have asked yourself the question before. So what is the definition of the band gap? I will come to it in a few lectures. Next week, I think I'll come to it. On this week. Anyway, it's overall the whole brilliant zone. When I say the band gap of a system is 2 eV, not at gamma point. When I say just of the whole system of this material is 2 eV, it means I check the whole band structure in all band directions, in all directions of brilliant zone, and they found the smallest distance between the conduction and the valence is 2 eV. I can bring you some examples next time. I wanted also here, but I forgot.
Let's go over this and I think you'll get it.
Okay, so the band structure is defined for every point in brilliant zone. Every point. It has its dispersion and everything. It's very hard to draw it for every single point. That's why I use symmetries. So I draw it along specific directions. Here I just drew 2 random like that, not even specifying the lattice. But the idea is when I plot band structure, I always do it along many directions to be sure that I went through everything, symmetrically covered. So I won't cover every single point, obviously, but I will go, because it is at the high symmetry points where you normally get minima or maxima of the bands. And I'm looking for that. So the high symmetry points, they don't have always this condition, like at the gamma, but they're usually the points of maxima or minima. There is a theorem of that, based on symmetries. So when I plot for all the special points, I'm able to say that I kind of describe the band structure. And then I look along directions between those high symmetry points, and I'm looking for the trends. And for the band gap, I look overall. And if there is just one state crossing the Fermi energy, that's it. Maybe it's not a good metal. Maybe it's like has just one state in the whole brilliant zone which will cross. It won't have electrons to screen something, for example. It's not a strong metal, but it's a metal. I mean, this is what I'm doing for research, so I'm kind of a bit hurt that this thing goes ununderstood. So ask me, I mean, really, I can explain to you, give you examples. I didn't realize that this wasn't clear. But okay, I mean, the point is to learn. It's not about the grade, because you guys will get a B, A. In the end, it won't be so important. You will go to some interview, they will ask you to derive one of the simplest things, and that will be the difference. And you know, it's very hard to review everything before the interview. But the things you truly understood, just know them. They're trivial for you. So that's why I'm saying try to really get to it. Don't worry about the point in the exam. It's more important you learn and you have it with you. It's your property, it's your asset now. So don't worry about the grade too much. I mean, yes, you try to optimize it, but
Excuse me.
yes.
Oh, I'm thinking of, okay, I know those sketches are like...
Oh, sorry, this is a terrible.
Yes.
I'll
But
bring
I'm
the band
thinking,
structure.
Isn't there a way where, isn't there a situation where, because here they have said in the middle of gamma x, there is, so can we...
Can be anywhere.
Crossing, can't it be like automatically in the middle? It's not...
I mean, yeah, normally gamma and x is a special point. So you will have a maximum minima here. It can be like going like this or something.
Yes. So can you have these things? I mean, how did you do the Fermi energy there? No?
You have to know the feeling. You have to. I mean, this sketch means nothing. I didn't specify how many electrons. I just showed you. Let's say you have this band structure. This is not Dirac. This is just. I'm saying that having a gap at one special K point means nothing. The system can be metal, and most often it is, because can you imagine that you have electrons at the Fermi level at every point?
Okay.
I've never seen it.
Then,
So at some point you will have a band gap, but local, I mean, at that point.
isn't it possible to take averages of the band gaps along the whole thing and judge that?
Not the average. You take always the smallest one, the smallest band gap, because
It becomes
this will
the
define
general
your properties. The smallest one will define. It's the minimal energy you have to put to transfer electron to the conduction. So the importance is of the minimal distance.
Does it mean that, for example, for this question, I would consider the one electron volt, and I use this condition to judge that we have the same conductor?
No.
Because you told me the minimum, which is one.
But I'm telling you, you have a state at the Fermi energy. As soon as you have a state, I don't care, because you're looking for the smallest distance between conduction and valence, let's say. Conduction and valence. For the smallest one. And it's 0. Because you have a state at the Fermi energy. So you check the whole band structure, and you check for the smallest band gap. But as soon as you have a state at the Fermi energy, there is no gap. In 2 lectures I will come to the band gap, so I hope then it will be a bit clearer. Where are we? Number 8, Rabindra. Again, this one wasn't supposed to be trick, but I don't know, quite a few mistakes. I don't know, I mean, what happened with you guys? You get scared of the exam, or... I mean, this one was almost identical to the one we did in the class. And still it wasn't that, I mean, what confused you? What was the problem? Well.
So if this is a brilliant zone, any vector outside the...
So actually we have a cubic here, but you're drawing a square, which is fine. I mean, but just know we have cubic, no?
So any vector G can be written as the nearest this one plus K brilliant zone, right?
Yes.
Any vector R plus brilliant zone. So Z can be written as R plus K brilliant zone. So in this question,
We are giving a point within the brilliant zone,
within the brilliant zone.
and
So
which
we are
of these
given
points
KBZ.
outside actually belongs to that point? Would have the same band structure, would have the same energy, no? This means that.
1 by 4, it's 1 by 100, 1 by 2. This is given, and we have to find G. We have to find this G vector. So it will be
So it's a cubic lattice.
cubic lattice.
It's a
So it
reciprocal
will be
vectors.
2 pi over A, and this must be an integer, certain integer, n1, n2, n3 plus pi over A.
I mean, in some generations I was
1/4.
giving here FCC lattices, which is more difficult to do, and
1/2.
or BCC. This was a simple cubic. So I have to translate by 2 pi over A in each direction, n times that, minus, plus, whatever.
So we have to check with this 3 vector whether this condition will satisfy or not.
Okay. Yes.
So in first case, it is 2 pi over A, 2 pi over A. It will be 1/8, 201 divided by 200, and it will be minus 1/4 plus.
I have to say it's not
No.
the easiest. 200 by 200.
No.
Can you just act as it is? I mean, it's maybe, I mean, to me it was easier this way, but okay. Everybody has preferences.
So it will be 2 pi over A, this pi over A, 1/4, 2.01, minus 1/2. Pi over A, 1/4, 1/100, 1/2.
No, actually, this one should be equal. This is the result. This is what you get outside. Should be equal this plus this translation plus some translation. Can you find translation?
N1, N2, N3.
I mean the combination of the primitive reciprocal vectors, which will bring you to this point, starting from the point within the brilliant zone.
1/100. Okay.
So can you find it? This one remains unchanged,
Yeah.
which is fine. Here you go, let me write it. Here
0.01.
I go 2 times 2 pi over A, which is fine. Here I go by pi over A, which is not a translation vector. So this one cannot be written. No, how to? This one is not, obviously it's not. Let's see the second one.
In second one, it will be pi by A, 9/4, 1.99, 1/2, and with the same this vector plus translation. I think in this case also we don't get.
So 9 quarters, 1/4, it's 8 quarters, it's 2 pi, which is good. This one is,
1.99.
No.
this one is not.
No.
If it was negative, yes, minus 2. This one is good because it remains. And then the C1 it is, but okay, we have to check it. Let's say, I mean, put in the exam, if you eliminate for sure two answers,
1/4.
it's, unless we made a mistake in the exam.
So in this case, we will get the vectors.
Yeah, it's negative here,
Yeah.
and also here it's minus 2 pi. So, I mean, do you all understand this? You made a mistake, I don't know how and why, but it's not difficult. It's just really knowing what is the primitive vector. Thank you. And number 9 was a disaster, Joe. I mean, number 9 you should have answered correctly. I mean, without any knowledge, without anything. What is the solution? 9. Can you come? I mean, come. Here, let's see. No, but I thought it was too easy to give you this problem. I mean, I thought it's really too easy. I'm not testing you enough. Can you write the block state definition, how on the form? You want this one? You could just go mathematically from here, because I gave, if you just plug in the formula, you'll get it. Or you could just think what it means. Yeah. And the charge density is defined as the absolute value. Oops, what is this?
There is no I.
What is this? Okay, the block state. So this is any k in the brilliant zone, and then you have a periodic function. This one is fine. It's the periodic with the lattice constant of the crystal. this one is the problem, because K depends on which K you're plotting it for, and it makes it non-periodic. This phase is a problem. But then I tell you the charge density. So can you make the charge density the absolute value? So even if you don't think at all, you plug it in the equation, you should get it mathematically.
It's a whole square. No, whole square means it's the conjugate.
So you get the conjugate times. There is no phase. All you are left with is the periodic part. But I mean, then I ask you, you have a crystal, let's see 1D crystal with core potentials. How can electronic charge density have any different period than the one of the crystal? I don't know how many got it right, but not many. If any, I don't remember. I was quite, you understand. But not just the mathematical part. Just if you have, it's atomic thing, how many electrons it has. So it depends on each atom, it will have some distribution, I don't know, but it has to be symmetric. Symmetric with the lattice. Okay. This was not supposed to be a big trick. I thought 6 would get it right, 2 would not think, but it was not quite that. Thank you. So my goal is to find problems which are actually easy, but will make you understand that you don't understand something, which is fine for the midterm, but not for the final. I'm happy to learn also then, but not at the expense of getting a first grade. Okay, this one too. I think on this one there was one solution correct, maybe 2, I don't know. Who is next? Nika? So, if you made a mistake of studying just from the previous midterms, you would have missed this one because I gave it for the first time. This shape, this type of problem. So, can you just draw the Fermi-Dirac distribution? Okay, you can write it also, but yeah, I meant more drawing because this is easier to. And right away, I'm asking the way you are drawing, writing, what is the value of this distribution? Exactly the Fermi level.
It's 2 or
1 by 100. 1 by 2.
Is it? Sorry.
Yeah. This is 0. This is 0. 2 by 2. It's 1.
2 by 2. Sorry.
Yeah. Yeah. This is not in the exponent. This one.
Sorry.
But this one here, how does it depend on temperature?
No.
Doesn't depend on temperature. So here, if I have a T0, it will be like this. If I have at any T, it will, well, this is not drawing, but it's my type of drawing. It will always pass through this 1/2. So this is one of the symmetry properties of the Fermi-Dirac. If you had drawn it and understood this, and I think I mentioned last time it's 1/2 at the Fermi energy, but I was counting very fast. I thought you analyzed this. So it's changing here with temperature. I mean, of course, if the state is very deep valence state, if it's here, we'll feel very little. But still, it will change more than any core state or the Fermi level. If it's at the Fermi energy, very close to the Fermi, but not at the Fermi, it will change a lot. So it's the valence state. Thank you. Everybody understand this? So was this a trick question? Tell me honestly. It happened to be a trick question because you all lost points there. But did you find it difficult, this question?
Yeah. I tried even to come up with a sketch, but I messed up on the sketch.
Okay, the sketch, I told you, you have to draw it yourself. Start from the function and analyze the function. What's the limit? At this value, at very high energy, how it's changing? I mean, you have to go through the exam. Better if you do it before the exam, but you have to do it now, after the exam. You have to do it. You won't understand unless you draw it for yourself. If you just repeat drawing from the class, you will get one property, not the other one. So it's essential that you draw it yourself and see how it changes and what it means. What is the next one? One for Carmen, William. Well, you can also just read it. I mean, for this one, I don't see what to write.
For the description of the crystal properties, the bond common boundary conditions on the work functions are expected to be most appropriate. Here I put part C, objective C, as the correct one, because...
Did you get surprised it was correct one?
No. At least I tried to relate with what they gave us in class, whereby we have, okay, we consider an infinite crystal, and then you take L to be N times A. Now for very large N, those conditions really work.
Yes.
Yeah, so that's why I put
Yes.
C.
I mean, this is essential to simulate bulk properties and to make it, so you have to have large N. Also, if you have very small N, your delta K is huge. I mean, doesn't make sense. Your delta K is half of the brilliant zone or something, doesn't make sense. Because that N determines the delta K within the brilliant zone. It's good. 12? Okay, 12, maybe the spin part confused you. We gave 1/2 to somebody, I mean, because got everything right, but not the spin part. Voila, can you come? It's the meaning of the density. Or if you want to pick, we can make Nishan solve it. Okay, Nishan, you come this one, and you'll get the third one. It's the same. I mean, you got it right, no?
Yes.
This one. Okay, so it's faster because the time is going. We won't do much of the problems.
So,
I was hoping to do problems a lot.
So this is a 0K problem. The electronic density charge will be starting from value 0 at the energy of 5 electron volt below the Fermi energy and reaching the value of 4.
Here it's the meaning of the density of states. A really application if you understood what it means, density of states. There was no asking you to memorize, I mean, you have to know it, but what is the free electron density of states in 1, 2, 3? Just to apply the knowledge of that, what it means.
Okay, so we don't have to worry where it starts or where it ends. Just focus on EF. Let's say this is EF, and it is somewhere here. And 5 electron volt below Fermi energy. Let's say this is.
So it's a whole valence band, let's say.
Minus 5.
It's covered
So
usually.
we also don't need to worry about the case. Like, let's draw it like this.
So
It says
why is it
linear.
important it's 0K first? Why is it important to know it's a 0K temperature? It tells me it's enough to go to the Fermi energy. I won't have any states occupied beyond Fermi energy. So I know I'm taking all the states.
So this is our.
Is this a metal or insulator? If you have
At least one, so it's a metal.
If you have a non-zero density of states at the Fermi energy, it's a metal. No? You understand that.
Okay, so density of state is like represented like this by board line. We don't know anything, we don't have any information below this point, which is EF minus 5. And so this is density of state. It means how many states are there per unit energy and also per unit spin. So the problem here is, I was also a little bit confused.
I realized that it
Yeah.
was.
So per unit spin here means per unit electron, because we count electrons as spin because electrons may be up spin or down spin.
Yes.
So in one state there are 2 electrons.
Yes.
So we may either count the number of states or.
So we will get here for one spin, let's call it for spin up, and we have to multiply by 2 to get the total one. But we gave a half point who did just the spin part wrong because that wasn't really done in the class. it should be clear from the problem, but okay, still got half point if you got it right without the spin. Okay, so how many states there are?
So how many electrons actually?
Yeah, electrons. Electrons, okay.
So it's 5 and this is 4.
So you want to find the area of this triangle.
So this is 5 into 4. 5
And 1/2 of that, no?
But
It's
then-
a triangle, so it's 1/2 times, which is 10. Okay,
10 states, but
10 states per spin up. For the other spin, 10 more.
yes, like I actually directly like
Put these two in
put
front.
it here, take 5
Okay.
into 4 because
Whatever.
here since it has been given per spin, we don't have to worry about states. We
Yeah.
start counting the spins. Actually, yeah, we should worry about the state because this is density of state. But since it is problem specific, so I directly started counting like a spin one. Like one state has 2 spins. I had that in mind before.
Because it says it's not spin polarized. So it has exactly the same number of spin up and spin down electrons. That's given here to help you.
So
But
there
okay.
are 10 states, which means 20 electrons. So since we are asked how many electrons, it would be 8. That would be 20.
Is it clear now to everyone? Huh, Joel?
Still don't get it.
Okay, here it's a density of states, per EV per spin. It can have 2 spins, up and down. I'm given the problem, it has equally many spins up as spins down. So I will find how many spin ups there are from here. Density of states, this will give me this area, will give me number of electrons because I will multiply energy times density of states, which has this dimension. So I will do like states per energy times energy. I will get 10 electrons per spin. Then I multiply this by EV, okay? Then I have 2 spins, 20 electrons. Huh?
Actually, from 0 to 5. From 0 to 5.
I mean, you define, you get density of states defined. This is all there is. Nothing else is mentioned. Your density of state is from here to here defined, nothing else. Everything else is 0. So the only non-zero density of states is in the range 5 eV below Fermi to the Fermi level.
And also we don't need to go beyond this because this is a 0 temperature
Yeah.
problem. So it is just this area where everything happens. Where we put all the
We don't
electrons,
have
there
any
are all the
states beyond the Fermi level. Okay, thank you.
Yes, thank you.
So you got it now? Good.
So should I?
Yeah, but then, I mean, Harriet?
In the plane wave method, you will largely need a larger plane wave basis set for an accurate description of the valence electrons of transition metals.
Larger, what does it mean, a larger plane wave basis set? That you will need more plane waves, higher G maximum, a larger, more plane waves to describe what? Alkali, transition, or alkaline metals.
More smooth side.
Yeah, so you will need fewer plane waves to describe something which has more nature of a plane wave, which is S or P electron. This is clear as a concept, no? Now, it did ask a bit of knowledge, what is alkaline, what is alkali, but this was done in the class, I just said. Alkali has S, one S. Alkaline, 2S. Transition is D. Do you know all that?
Actually, ma'am, I even didn't know the atomic number of all these.
No, but there are even examples. Nickel or iron, I mean, they're not S elements, they
So
are
we
D.
didn't have this in mind.
Okay, but we anyway scaled 1 point, maximum was 19 points. So we
Like,
gave an
I
extra.
knew like what kind of wave function would require more plane waves or less plane wave, but yeah. I
Okay,
should
no,
have-
it's okay. But we scaled. There was one taken for everyone. You didn't know this, somebody else didn't know what's formal unit, so one was taken to make it a bit better for you.
Previously, the pattern alkali, you have said alkali has S, and
Yes.
then alkaline
It's the
has-
very first column in
then
the.
alkaline,
It's the next one. 2s.
2S.
Do you know how it's filled? The levels, atomic. I mean, this is very important.
Also,
That's not just chemistry. Hund's rules, but it's not just chemistry. It's the basics of the structure of
Things to do with
configuration.
SP and so on, I need it.
So first one just S, second one 2S, then you have P on the right, and then you have these below. If you don't know it, we can discuss it because it's really important to understand. So the answer is, knowing all this, B, because it's the electrons, which are very far from being,
more smooth.
yeah, well, smooth, yeah, not plane wave, like, and actually called smoother, okay, depends. In energy, they are smooth.
Because like,
They're more localized.
yes.
So, I mean, depends if you think the energy is smoother. The energy is more flat. Okay, Vala, can you come to the blackboard? This one actually, one can go and solve for the Fermi wave vector, but it's an overkill. So, lithium and sodium. So it's given in the previous problem, if you're not sure. It's the alkali metals. They're S electrons. And for them, free electron approximation is valid. That means that they will have a spherical Fermi surface. Okay, spherical, which is easy then. I don't even have to find what is exact KF. I know it's one electron. So what is the, you know how it depends and how? So let's say this, let's just write the volume of the brilliant zone is equal to the KF cubed. This looks like not equal. Why? Okay. So this volume, this KF will depend on the volume. And the volume of the brilliant zone depends inversely with A. Do you agree with that? It will just depend. They have the same structure. Are you asking a question or no? They will have the same structure. So I don't even care to know what is the definition. It's just proportional to A cubed. Proportional. I don't care of anything else. One electron is the same. The same lattice, it's a, what is it, BCC. I don't care. And KF cubed is proportional to this. So the larger the A, the smaller the KF. Okay? Or you could just go and solve it if you want, if you have time, it's fine, I don't care. So lithium was the answer. Also number 15 was not, JC, can you solve it for us?
Number 15, consider a semiconductor which can be doped with electrons if the Thomas Fermi screening stronger in the dope or undoped case. My answer was A, and the reason is I just used the equation delta n naught over n naught is equal to negative delta v naught, I think. And from there, I imagined that if I increase the number of electrons by doping, I will decrease the value of the strength of it.
Okay.
So I
And
answered.
that's one way of to reason, but I mean, naturally, you put electrons and their function is to screen the core. So you have more, you feel the core potential less. I mean, that's that simple. Even without any formula, you could solve this one. So adding electrons, you see less the core. It makes sense, no? Say yes, William.
See like this thing, huh?
I mean, you have a positive charge in the center. And I'm asking when it's screened better. When you have more electrons. you will see less the charge of the screening. The meaning of it is to feel less the potential of the positive core. The more negative you put around, the more you feel the core.
Maybe I just didn't understand what the doping means, because I thought that by doping...
Okay, I didn't
basically
complicate.
adding-
Yeah, it depends if it's metal, if it's metal. It depends on many things. So I did not put it in the problem. I'm just saying you add electrons, imagine at the Fermi energy.
So we take it like doping is basically adding in electrons. I thought that...
It can be
adding
holes or
impurities-
electrons. It can be
Yeah,
many
yeah, yeah.
things. But here it specifies electrons, no? Yeah, with electrons. It's the simplest possible. I did not complicate it with anything if it's what it is. You just add more electrons which can move to screen the charge. This is the only thing, it's the simplest possible case. Okay, and now the problem.
Excuse me.
Yes.
It's okay for me like mathematics. And I was saying that when doped, it means that you have a bigger N naught. Chicken from this one is given by this. So I thought that when you dope, then you just start increasing the N naught. And for that matter, then the term becomes bigger. And when it is bigger, I expect that this one now becomes smaller. So I thought it was it.
Okay, let's talk later. But it's really simple. There was no need for formula. Here, just the definition, what is screening, essentially. The problem. Rabindra. So you all kind of came to a quite decent point. Mathematics scared you. I maybe should have written the problem differently, because what was, I was given 1.25 pi. Somebody forgot pi. Most of you did not write 1.25 as a fraction. If you have written it, you would have thought until the end. With 5 quarters, you could get to the number, easy number, to the end. So, but okay, in the end, we gave 2 points on the first part, on finding the right vectors and drawing correctly, and 4 points even, not just 5, 4 points in the B part, for the right condition, for the right implementation of the condition. Okay.
So this is
Then you draw the primitive vector, lattice.
both primitive.
Yeah,
ones.
both.
Okay.
Just to be, because people made
So
many
in-
silly mistakes.
In this case, B is less than A.
Yeah, okay. With this, it should be clear how I had to take half point on the first part if we didn't take this into account. Yeah.
So this will be A1 and this is A2.
Yes. Okay. This is
And
the
this
primitive.
length is A and this length is B.
Good. Okay. And now the B vectors. You can just read them even. You don't have to. I didn't ask you to actually even calculate it. Just to have them.
So
It
with
was so easy that-
AI Bj is equals to 2 pi delta Ij. Now we can find B1 and B2, reciprocal lattice vector, and it was B1 2 pi pi A 1 0 and B2 is 2 pi pi B.
If you're not sure about these vectors, if you have to derive them, play a bit more with it until it becomes so natural to you.
So in this case,
this should be really possible to write right away without any formula, without any derivation.
so in this case B1 vector is shorter because A is larger.
Yes, yes, and this is
So-
the point that half of you missed actually, which is a pity to lose half a point on that. It's silly, no? It's B less than A, it means that 2 pi over B should be longer, so it should be this way, rectangle, not this way or not square.
This is B1 this is
Yeah. And now construct the brilliant zone here.
so the brilliant zone I draw here. So
Okay, it will be the half of this and
half of this.
and
It will be like this.
yes,
This is the brilliant zone.
fine. So this is 2 points. And then the B part of the problem.
B part is we have to find the ratio of B by A, for which the entire brilliant zone is within the Fermi circle,
And
the Fermi circle touches the brilliant zone.
okay, here I see some people misunderstood. So they got 2 conditions.
Yeah.
I was really trying to understand how you came to this. Anyway, you solved correctly. You just added a bit more work to yourself, having to like 2 kinds of problems. It was meant simultaneously, because if I just say that B over,
Now I understand.
because if you just say that the brilliant zone is within the Fermi circle, it can be here. I have to put a condition, it's touching. It's within and touching.
Touching.
So it's all like, it's 2 conditions for the same situation. Huh? You understood?
Yeah, I got it right. However, I got somehow confused on because if you are considering the Fermi circle and you have a rectangle, you cannot have a circle that touches both. I mean, it's not
Okay,
possible.
draw it now. Okay,
In
actually,
this case, we can touch
Let-
only one.
let's make it
Yeah, it has to
more like
only touch one
rectangle,
side.
so it's more clear.
Yeah.
Okay, so how do you draw here the Fermi circle? It's not easy to draw it very well.
Okay.
So can we draw it like this?
It's
No.
easy.
Just touching the one point and drawing a circle.
No, because the circle
or-
has to be centered around the gamma.
Okay, so it will be like this, like an
That's not a
ellipse.
circle.
No. It's always, it's a free electron.
Mhm.
So it has to be circle.
It has to be circle, not ellipse.
So, now, my drawing skills will come. Okay, it's really hard to
Yeah.
draw it well.
Mhm.
But you imagine, do you see it clear? I can try, I can make an effort to make it better, but it's not easy to draw. I'm warning you, it's not.
But madam, geometrically, is it possible?
Yeah, possible. You can draw
I mean, in
rectangle
any
inside
circle, okay, I'm putting a circle here.
I see for for a square, it's very possible. For a
No,
triangle,
but it's one touch.
possible.
William, you have a circle.
Yes.
Can you draw a rectangle which is touching it within? Sure,
Yes.
we can always place it.
Okay, maybe from that perspective, it's fine.
I mean, you can make
Now we can
this.
start from the square and try to do this.
Okay,
Yeah.
okay.
We can
It's also here. I mean, it's not easy to make it perfect circle, but I think you're getting the idea, no?
All the possible solutions will be there, like while like going from square to a line, it will be
Okay.
included.
So, is this part clear to everyone? What was the condition?
Yeah, I get.
That the Fermi circle is touching, but you solved it actually.
No, I saw.
You make a problem, but you got almost full points.
Yeah, I got the point somehow.
And people lost points actually, and they are happy.
Yeah, because.
So the Fermi circle is touching the brilliant zone, and the brilliant zone is within the circle. So this is the only way to get it.
So this will be the radius of circle.
That's clear to everyone. That this here is the radius. I'm
Radius.
just applicating.
And we have to find the ratio of B by A. And for this, pi, and we have to calculate the.
Okay. Let's write first KF when you already
Yeah.
do it. Let's write the KF.
So KF, this is KF. KF will be equal to coordinate of this. If you know the coordinate of this, we can calculate the.
So it
will
is
be
the coordinate of the edge of the
pi
brilliant
by
zone.
A, pi by B.
Okay. Okay. Is this point
This is
clear to everyone?
0.
That what is the coordinates of this? Okay, good.
So KF will be the square root of pi by A square plus pi by B square.
Can I write B over A as whatever you want, X or whatever? So we just write, we solve for this X. So,
There is 1.25 pi electrons per primitive cell.
yeah, If you do it in fraction, it's much easier. I'm sorry
So-
you do it. I thought you would realize it. Sorry. Because I wrote 5/4, but then it looked like 5 was with 4. Oh, it's too bad. I wrote 125, which actually made you not finish the problem.
So the circle with this
So let
radius.
me write. N is 5/4 pi.
You are writing n like that.
Mm-hmm.
So it will be 5/4 pi 2, because you have to consider this.
But not
into-
42.
Not 42 into
Uh-huh.
and area of this one. So it will be 4. It will be pi by a pi square by AB.
2
4 pi.
2 pi squared, okay. 4 pi squared.
4 pi
Good.
square by AB.
So this point clear to everyone?
Yes, yes.
Okay.
Now we substitute the value of kf. It will be pi square by a square plus this will be cancelled out. It will be 5 pi cube upon AB.
No.
This will
There is
pi
still-
will cancel out.
There is still 2.
4 by 2, 5 by 2.
Okay, now let's introduce this x so that it's easier that you right away see the then b is equal xa. Can you introduce it inside?
Okay. So it will be 1 by a square plus pi by 1 by b is x square, a square, divided by 2 a x 2x a square.
Yes. Good.
So all a square will cancel out. So it will be 1 plus 1 by x square is equals to 5 by 2x. Right? So it will be
What is this? What you're writing?
it's or
Okay. I've never seen it. Fine. It's equivalent, so it's the same thing. Fine.
It's very famous in Nepal.
Really? I've never seen it.
this two are this or this equivalent.
It's true. No, I don't complain. I was just curious.
So it will be x square plus
Multiplied
1
by x squared.
by x. I can
No. Just multiply everything by x.
Okay. I write 5 by 2x.
But wait, what?
No, it's fine, it's fine.
No, don't confuse me. It's not difficult. I will write for the class like this. And then you get x squared plus 1 is 5 half x.
X.
And now you can solve this equation
This is
with
our
finding
now-
the roots.
What that equation?
Yeah,
That's
we
okay.
write nicer that it's clear what is A, what is B.
minus plus 1 is equals.
Okay. Oof. I wrote it like.
So x will be
There are two solutions.
5 by 2 plus minus square root of
So this is 1 or 2 solution,
2.
2 together. So what is b squared?
b square minus 4 AC is 1. 1 divided by 2a. So it will be equal to this 5 plus
So you came to the
minus
end?
square root
The
of
I didn't evaluate the square root.
Yeah.
You can scale it with the numbers.
25 by 4 minus 4.
Yes, ma'am. Like,
Yeah, that idea
my-
of x is kind of.
like I'm a little bit
Scared.
not scared. Like I'm a little bit kind of irresponsible with this kind of thing.
Yeah, but here there were 2 solutions.
Yes, ma'am.
I didn't know that you understood which one you have to choose. I had to take a point off
Yes, ma'am.
because there was plus
And
minus.
also in this case, like I wrote,
Yeah.
like,
okay.
yeah.
I mean, but
Yes, I
it's
know.
not a square. It's
Yeah,
not.
no, I know, ma'am, like I have mentioned it.
Yeah,
here,
yeah,
like,
but-
yes, ma'am.
But okay. So it's a nice number coming out. You see, it's not. And here there is a condition that b is less than a. So only one solution will be good. It has to be this one.
This one.
So this was also a half point, getting the right sign of the solution. I don't think anyone got it as 1/2 in the end. A few of you came quite close to it.
Yeah.
But
It was
is it
pretty
okay?
close.
Do you understand? Yeah. It's not, I think, very difficult. It's a bit more than what we did last time in terms of mathematics, but the condition, a few of you didn't get the condition. Or you got the condition and got the wrong, you put this or this as the in the condition. Thank you. Okay, the class is just finished. If you want, we can stay solving a problem. If not, I'm doing it for you. I'm not pushing you to do it. If you have a class at 11,
Another classes.
as you like, you tell me if you want to solve something or you want to go to the class.
We have a class, however, if you could.
You want to solve something. You have class here or in the next
We
room?
shall have it in
Wanted
30
to
minutes.
Get something.
You tell me. You want to leave, you leave. I mean,
Can
this
you
part
pass on?
class is finished. Now, if you want to stay,
When are we going to have this class next? Like tomorrow?
Tomorrow. Tomorrow
is-
morning.
Okay.
but it's a lecture. We are starting with the new things. I mean,
Okay.
I'm teaching new stuff.
So Nadia ma'am won't come from now? Or?
I think she has one more lecture.
Okay.
And you don't call us ma'am, you know. It's by name is fine. In physics, in science, it's.
It's very.
I know. I was called ma'am, Natasha, ma'am. Like a few people couldn't make it until the end. They kept using it, but or even calling me sir, which was even more confusing. So let's say so. Who wants to leave? You leaves, and we can solve something a bit easier for the whole class. So you tell me. I also want to go take coffee. I mean, I don't have any problem with leaving. Yeah, please give me the exams. Yeah, this is important. This is.